Hello again, grade 8s. In today's lesson, we are going to look at analyzing linear graphs, which is something that we're now ready to do, considering how we spent the last couple of lessons looking at taking a linear equation, using it to complete a table of values, and then from the table of values, plotting the data on a grid. And now that we have the data plotted on a grid, we can start to examine the data in a little bit more detail. First of all, we're going to look at distinguishing between what we call discrete data and continuous data. So the graph I'm going to use here as an example is, it says field trip supervision. So on the x-axis of the graph, it shows the number of teachers. And on the y-axis of the graph, it shows the number of students. So what the graph is trying to show you is like if you have like a certain number of students, how many like field trip supervisors would be required. But let's talk about what discrete data is. Okay, discrete data is data in which only a finite number of values are possible. Now what this means is some values in between recorded data points actually don't have any physical meaning, or they're not physically possible. And typically, if we look at a value that's not a whole number, we can identify very quickly that if it makes physical sense or not. Okay, so let's look at this graph here. So on this graph, on the x-axis, we have the number of teachers. So 1, 2, 3, 4, 5, 6, etc. Now, discrete data tells us that if we look at in-between values, they have no physical meaning. Okay, so let's say we looked at this. Here's 1 teacher. Here's 2 teachers. And we looked at like an in-between value right here. Well, on the x-axis, that would be a value of 1.5. Now the question is, does that make any sense? Could you have 1.5 teachers? No. It's either you have like a teacher or you don't. You don't have like one teacher and then like just the legs of another one. Okay, it's got to be like a whole quantity for it to actually make any physical sense at all. So what we'd say here is we'd say the data is discrete because, for example, you cannot have an in-between value. So in between the number of teachers 1 and 2, if we looked at 1.5, that wouldn't make any physical sense. Because in terms of talking about people, you have to have a whole number when making a reference to them. Okay, so that's what it means for the data to be discrete. Now, in this situation, it's not actually appropriate to draw a solid line through the data points. I know in the last couple lessons we had been doing that, but it turns out in the last few lessons we weren't looking at any data that would have been classified as being discrete. So if the data is discrete, as in like in between values are not allowed, we don't want to do a solid line. What is acceptable is to do a dashed line. So a dashed line would just look a little something like this here. So instead of having like a continuous solid line, you have little gaps in the line. The little gaps in the line would just tell you that not every single value on the axis makes physical sense, okay? And that's what discrete data is. So if you looked at in between values, do they make any physical sense or not? Now let's compare this to continuous data. We'll use a different example here. So the graph says cost of banana chips at a bulk bin in like a grocery store. So on the x-axis, you have like the quantity of the banana chips that you're going to like scoop out into a bag, presumably. So we go up by like increments of 100 grams. And on the y-axis, we have the cost of the banana chips, and it's measured in units of cents. Continuous data can take on any value within a specific range, like within reason. In between values here, they actually have physical sense. So if we looked at this graph, well, let's say we took like on the x-axis 300 grams and 400 grams. And let's look at an in-between value like 350 grams. Would it be possible to go to the grocery store and scoop out 350 grams of these banana chips? It would, okay? You can definitely get 350 grams. Even decimal numbers would make sense. You could have like 345.02 grams, depending on how many of the chips you actually took out. So in this case, because in between values on your axis are allowed, we refer to this as continuous data because my in between values have physical meaning. So the example I said here is data is continuous, since you could, for example, if we looked between 100 and 200, an in-between value would be 150 grams. That number makes physical sense. You can scoop out 150 grams of the banana chips. In this case, because the data is continuous, it's okay to draw a solid line through the points, okay? Because there are no gaps in the data. Like, any data point is going to be allowed, or any value on the axis is going to be allowed. Now, I said up here within specific ranges. Like, obviously, we're not going to scoop out 100 million grams of banana chips. Like, that would just be absolutely absurd. I mean, you guess technically could do it if there were that many banana chips on the planet Earth, but within a specific range, the numbers need to make sense. But if you look at in-between numbers for continuous data, they're allowed. And that's the difference between discrete and continuous. Discrete data, in-between numbers, don't make physical sense. And then continuous data, in between numbers, they do make physical sense. Now, part of the reason that we like to draw these lines through the data is it allows us to make predictions about certain values that we actually didn't collect with our data points. And there's actually two different types of ways we can make predictions about different values: extrapolation and interpolation. Extrapolation involves making a prediction about a value that falls outside of the range of collected data. Okay, so let's go back to this graph. So this is the one where we had the student to teacher field trip ratio. And we drew a dashed line through this one because the data was discrete. Again, in between numbers don't make any sense. Can't have 4.5 teachers. Now, what you can do is you can use the line to make predictions about points that we didn't actually plot on the graph. Like, let's say, for example, okay, I'll pick a different color here. So let's go with, actually red's fine. Okay, so let's say I wanted to know, if I had 5 teachers, how many students could actually be supervised. Well, the way I would determine this is I would start at 5. I draw a little bit of a broken line up to where my line is, okay? So all the way up to the line. Okay, so the line ends there. And then I could go all the way across to see the number of students that are allowed. So here, actually, I think I actually did this with WordArc. Yeah. So if you had 5 teachers, okay, what I could do is I could use the line to predict how many students would be allowed on that field trip. So what I do is I draw a vertical dashed line up to the line I've drawn through my data points, and a horizontal line over to the y-axis, and it tells you that 30 students would be allowed. Now, this is what we call an extrapolation of our data points. So if you look at the graph here, the last data point I have on the graph is this point, okay? Now, if we have any predicted value that is outside of my last data point, or actually if it's outside of my first data point, okay, so anything in this region or anything on the outside of that region, that is what we call an extrapolation. So an extrapolation is a predicted value, but it falls outside of the range of our plotted data, okay? So again, my biggest value for plotted data is this point. So because we went outside of that to make a prediction, we call that extrapolation. So in this case, the line can be used to extrapolate that 5 teachers could supervise 30 students. Now, we can also interpolate the data as well. Interpolation involves predicting a value that's inside the range of the collected data. So let's go back to this graph, the one that dealt with the banana chips, the amount that you are going to scoop out and what the cost would be. Now, let's say that I wanted to know, okay, how much would it cost for me to have 350 grams of these chips? And by the way, that's okay. That makes sense. An in-between value here does make sense. So we want to predict how much does 350 grams cost. Okay, so what we do is from 350 grams, draw a line that kind of goes straight up to the line we drew through the data, and then another line that would go across to the y-axis, and this would probably hit at somewhere around about 210. Now, here, the difference is that this dashed line I drew, this actually occurred within my data points, okay? So this is the spot where my data started. Here's a spot where my data ended. In this case, the extrapolation, the prediction we made, fell inside the range of the data points that I can see. So we call that an interpolation. As opposed to this previous one, my data started at this spot and it ended right here, and we made a prediction outside of where I have the data points, and that's what we call an extrapolation. So in this case, the line could be used to interpolate that 350 grams of chips would cost 210 cents. Okay, let's practice this a little bit though. Okay, it says example 1. The graph below shows the amount of money a person earns based on the number of hours worked. So part A says represent the data with a table of values. So let's start off by doing that. This is actually kind of like the reverse process of what we've been doing in the previous lessons. So in the previous lessons, we had a table of values and we plotted the points. This time around, we have the points and we want to construct a table of values. Okay, so here's my x-axis and here's my y-axis. Now, what I'm going to do here is make a table of values. So the first part of the table of values, the first variable you write in there is going to be the variable on the x-axis. So I'm going to write down the name of the variable, which is the time that's worked. I'm going to write down the symbol to represent it. If you look on the graph here, it shows a little t there. So that's going to be the variable to represent it. And then the units, we can look at the title there, are in hours. Okay, so let's start to create a table here. Okay, so that is my x variable or manipulated variable. Now my responding variable or the y variable would be my pay. So I can say my gross pay. So write the name of the variable, then a comma. What's the symbol for the variable? If you look at the graph here, it uses a capital P for it. And what are the units? The units would be dollars. Okay, so let's plot these points. Or let's not plot the points. Let's try to figure out what these points actually are. Okay, so to read these points. Okay, so this first one, if you go down here, it hits the x-axis at 1. So you'd have, when you've worked 1 hour, the y-axis, if we go across here, looks like it's in between 20 and 15. So it would be 1 and 15. The second point, if we go down to the x-axis, it would hit the x-axis at 2. And if we go across to the y-axis, that point would be 30. So if we work 2 hours, we make 30 bucks. This point, if we go all the way down to the x-axis, we've worked 3 hours. And then if I go across to the y-axis, between 40 and 50 would be 45. So this would be 45 here. And then this point, if I go all the way down, I'd hit the x-axis at 4. And if I go across here, I'll hit the y-axis at 60. And then the final point would be if you just go straight down and then go across. This is going to hit it halfway between 70 and 80. So that's going to be at 5 hours, 75. Okay. So that's my table of values for the different data points. Now, part B, this is a little bit different. It says describe the pattern that we can see in the data table. Okay, so this is part A. And this is going to be part B. Okay, if you look at the data table here, what I want to know is for every additional hour worked, how is my pay changing? Okay, if you go from 1 to 2 hours, so if you have an increase in 1 hour worked, so I'll write down here for every additional hour worked, okay, so if I jump from like 1 to 2 hours, how much more money do you make? Well, how do you get from 15 to 30? It'd be you add another 15. So for every additional hour worked, the person would earn $15 more. And this trend continues. If you go from 2 to 3 hours, you continue to add 15. Add 15 to get to that next number. To go from 3 to 4 hours, once again, you're just adding 15, adding 15. To go from 4 to 5 hours, add 15. So this actually tells you how much they're making per hour. So if for every additional hour worked, the person earns $15 more, I could actually say they're earning $15 per hour. Okay, part C, I'm gonna have to do this on the next slide because I just run out of space here. Okay, it says, is it reasonable to determine the amount of money the person makes when time is 3.5 hours? If so, find this value. Okay, so what it's asking here is it's asking, is the in-between value between 3 and 4, so let's just focus on this. Okay, is the in-between value between 3 and 4, which is 3.5 hours, does that make physical sense? Like, can you work 3.5 hours? Yeah, of course you can. You can work a shift that's 3.5 hours long. So let's classify the data then. If you can have an in-between value, like a 3.5 hours, does that make the data discrete or does it make it continuous? Well, if you can have in-between values, it would actually make it continuous. Okay, so let's try to like identify this here. So don't worry, we'll about the assignment in a moment. I'm just gonna write down the work here. So let's do part C. So it says, is it reasonable to determine like how much you make for 3.5 hours? And I'll say yes. Since a person could work 3.5 hours, 3.5 hours. So 3.5 hours would be when time is 3.5. The data would be continuous. Okay, now it says, is it reasonable to determine the amount of money they make for 3.5 hours? Yes. And it says, if so, figure out what this value is. Okay, so we're gonna start here on the x-axis. So at this position, that is 3.5 hours. And what we're gonna do is we're gonna use the graph to figure out how much you make for 3.5 hours of work. Okay, so now, first of all, in order to make a prediction from the graph, we need to construct a line. So if the data is continuous, this tells me I can actually draw a solid line. If the data was discrete, you can still make predictions. We just have to do it with a broken line. Okay, so I'm gonna go ahead and I'm gonna get a line here. So let's insert a line. Again, let's make it so I can actually see the thing. change it to blue. Okay, and let's go to my graph here. So let's get this guy to start at the origin. If you didn't work any hours, you're not making any money. Okay, yeah, that's probably about okay. Okay, let's make this line go through all these points here. Okay, that looks pretty good. Again, you can do this with a ruler. Okay, now we can use that line to make a prediction. So what I'm going to do here is at 3.5 hours, I'm going to draw a dashed line that goes up to this line that represents the data. So it goes up to here. And then we're going to hit this line, and then we're going to go across. So we're going to go across to here. And then where does it hit the axis at? Well, you're going to have to guess a little bit. I mean, it looks like it's closer to 50 compared to 60. So I don't know, maybe it hits it at like about $53. So we can say when your time worked is 3.5 hours, the pay, P, would be equal to, and we kind of eyeballed it at about 53. It is, by the way, exactly $52.50, but we don't need to worry about that. We're just making an approximation off the graph. Okay, now one other thing I just wanted to point out here. So what did we actually do for this data? When we did this, where we figured out like what is the pay for 3.5 hours of work, was that an extrapolation or was that an interpolation of the data? So extrapolation means that you made a prediction outside of my points. So here's where the points start. The points start here and end there. So did I make a prediction inside of those points or outside of? Well, I made a prediction on the outside. So that's actually going to be referred to as an interpolation. Okay, so this was an interpolation. Okay, now for this one, it says D, if the pattern continues, determine the number of hours that must be worked to earn P is 120. Okay, now if you have if the scale of the graph went up high enough, you could actually use the line to figure out how many hours of work to get 120. But the problem is like 120 would be like somewhere like here would be like 90, 100, 110, 120. It's off the graph. So we can't use the graph to determine how many hours would result in $120 worth of pay. So the other thing we can do is we can take the table of values and we can extend the table of values. Okay, I'm going to erase part B here just so I can actually do that. So I'll go to an eraser. That's going to get rid of this. Or attempt to get rid of this. It doesn't seem to want to let me to do it for some reason. Let's try this again. Okay, that's all right. It really wants me to guess to keep it on there. So I'll just pull it off to the side here. We'll do it like maybe over here. Okay, so what I'm going to do is let's pull it over to the side.
Mr. Oster, could you please call 2403, Mr. Oster?
I'm just going to extend the grid, okay? Okay, we'll just keep going. Ideally, you would do this directly below the graph here. Okay, so let's go below. So let's go to 6 hours worked. Okay, if you worked for 6 hours, you'd add another $15. So 75 plus 15 would then be 90. If you work 7 hours, you'd add another 15. So that'd be $105 earned. And if you worked 8 hours, you'd add another 15, which would be $120 worked. Okay, so that's going to be my solution. By extending the table, I was able to figure out that in order to earn $120, you need to work 8 hours. Okay, so let's fill that in. So I'll say when your earned pay was 120 hours, then you would have to work 8 hours to get that pay. Now, what was that? Is that an interpolation or extrapolation of the data? Well, it's a little bit tough to see because we're not looking at the graph here. But again, like if we were at 8 hours would be like beyond what I've plotted with my data. So extending the table of values would go beyond my plotted data. Therefore, this would be an extrapolation of the data. Okay, so that's it for this lesson. And you can complete the assignment called Analyzing Linear Graphs in the Linear Relations workbooklet. And then I'll talk to you in the next lesson.